Find the circulation and flux of F around and across C. I'm given a vector field F, x cubed y squared I plus 1/2 x to the 4th yj, and I see my path here in the plane where I travel counterclockwise around this kind of a loop where I start off on the parabola y equal x squared, travel from the origin to 1, 1, and then I travel back along the parabola x equal y squared from 1, 1 to the origin. And I could imagine just evaluating what I know to be these line integrals. The circulation, or flow, moving counterclockwise, so I might as well indicate that. It's just this, which I could think of in its scalar differential form. The flux, defined as F dot n, where n is an outward facing unit normal vector. I could calculate this way. And looking at this, I have a piecewise defined path. I'd have to do use additivity on both line integrals. I'd have to calculate 4 different integrals. The other way I could think about it is using Green's theorem. My path is piecewise smooth, right? It's continuous and differentiable in 2 different pieces joined end to end. It is smooth and simple, right? It doesn't intersect itself except for where it begins and ends. Closed, and it incurs a region R. It checks all of the boxes to get to use Green's theorem. So to calculate circulation, instead of this path integral, I could evaluate this double integral. So let's see if that's an easier approach here. So let's start off by finding some partial derivatives. The partial of n with respect to x. So n's the second component here, so I need to take its partial with respect to x. So let's see, that's going to be a 2x cubed y. And now I need to take the partial of m with respect to y. And so I look at the first component, and that's going to be a 2x cubed. Oh, those are the same. That's my component test for a conservative field. This vector field is conservative, which means if I'm calculating this path integral, I'm going to have to get 0. Okay, well, even if I didn't notice that, if I set up Green's theorem, I get a 0 integrand, which means I'm going to get 0 when I evaluate this integral anyway. So right there in the middle of Green's theorem, right, is kind of like, hey, if you're a conservative field and you go around a loop, you get no circulation. If this was a force field, I could say you get no work. All right, flux, I calculate this double integral. So I need to take 2 more partial derivatives, and this time I will have a more interesting double integral to consider. So the partial of m, here, I'll just set it up here. The partial of m with respect to x, I get a 3x squared y squared. Plus the partial of n with respect to y, I get 1/2 x to the 4th. So this double integral I actually have to consider. I'm going to imagine integrating first with respect to y. So my dA is going to become a dy dx. I enter the region through y equal x squared, and I exit the region through, well, y equals root x. Bounds for x that include the whole region, 0 to 1. So this is the double integral I need to evaluate to calculate the flux. So I'll write that on the top of this board, and we'll go from there. All right, so now we just need to integrate. First with respect to y. Okay, well, an antiderivative here with respect to y would be x cubed, y cubed. Excuse me, x squared. I lost track of that power. X squared, y cubed. Plus 1/2 x to the 4th y. And then evaluated from x squared to root x. Still have that dx out there. All right, well, now I just need to substitute in root x and simplify, and then x squared and simplify. So root x, well, that would give me an x times root x, so x squared, that would become an x cubed times root x, which is an x to the 7/2. Plus 1/2, and then I have x to the 4th times x to the 1/2, and so that would become an x to the 9/2. Minus, plug in that x squared, and that would be x to the 6 times x squared would be x to the 8th. Minus what happens when I plug in an x squared there. Already having distributed the minus that would come along with evaluating at these bounds. Well, now I just need to integrate with respect to x. All right, so I would get 2/9 x to the 9/2 plus, let's see, it'd be x to the 11 over 2, so 2 over 11 times 1/2, that's a 1/11. Minus 1/9 x to the 9th, minus, that's going to be x to the 7th, 1 over 2 times 7, 14, evaluate from 0 to 1. Well, I need to plug a 1 in, which means I'm just taking the difference of all of these fractions, and what we get, sum and difference of all of these fractions, and what we get is 181 over 1386. So, the circulation was 0, but the flux across the boundary, 181 over 1386. And there we have the circulation and the flux calculated using Green's theorem rather than by directly evaluating the line integrals.